everybody. Today we're going to pick up where we left off in the Chapter 4 notes. The last thing we did was we learned how to do free body diagrams, which are required for dynamics problems. Do you understand? They are required for dynamics problems. Now, since we're talking about problems at the moment, look at this technique. This is a process that you can go through, especially if you are having trouble getting started with a problem in order to find an unknown. First, you read the entire problem, and then, and this is a very important next step, you identify the motion of the object. What is the object doing? If the object is at rest or is moving at constant speed, then that means you're going to be somehow applying Newton's first law. Newton's first law. In other words, the object is in a state of equilibrium, and that's when Newton's first law applies. If, on the other hand, the object is accelerating, and that does include decelerating, then that means the object is in a state of non-equilibrium, and you're going to be applying Newton's second law. So you see, reading the problem and understanding the actual motion the object has is extremely important, because that's going to tell you which concept you're going to use, Newton's first law or Newton's second law, simply by understanding what the motion is. Now, once you've identified which state applies, equilibrium or non-equilibrium, then you identify any and all forces acting on the object, not forces acting by the object on something else. We don't care about those. We want the forces that are acting on the focus object. Assign each a variable. Use subscripts. Too many people do not use subscripts, and then they get confused. Well, if you do, you have only yourself to blame, because I'm sitting here telling you right now to use subscripts. Okay? Because you can have more than one type of particular force. You could have two tensions, as you saw in the free body diagrams. You could have two normal forces. Always use subscripts to distinguish. Now, once you identify all the forces that are acting on an object, then you're going to draw yourself a free body diagram. You're going to draw the forces. Remember, they are solid arrows. Guys, forces are vectors. They are not line segments. They are arrows. They must be solid arrows. Don't use dotted lines. That won't get you any points on the AP exam at all. Label those forces properly. Vectors on the AP exam that are not labeled don't earn points. Designate directions on your diagram for positives and negatives, just like we had to do in linear kinematics and in projectile motion. You need to let the person looking at your work understand what you're choosing for your directions in the different planes. Now, depending on which motion you identified in step 2, then you're going to set up either Newton's first law or second law to solve the problem. In some cases, you may need to use kinematics jointly with Newton's laws, and we've learned how to do that on the first page of the notes. If there are two unknowns, you will need two equations to solve the problem, and we will be looking at that. In other words, a system of equations. This is why they teach you how to do systems of equations in math class, so that you can use it here, okay? We'll talk more about that later. Today, I want to get started on talking about the 5 forces that we deal with in mechanics, basic mechanics. There's one field force and 4 contact forces that we typically deal with. Since there's only the one field force and it affects everything all the time, we're going to start with that and then look at the contact forces later. So the one field force that we're going to be looking at today is, of course, gravity. And if you'll remember, gravity is the attractive pull between one mass and another mass. Now, here's where we need to understand that there is a synonym term that we can use when we talk about gravity, and that is the term weight, if we're talking about a planet. On a planet, the gravity exerted on you by that planet is typically called your weight. So the Earth pulling on you right now is not only the Earth's gravity, it's also your weight. That means we can use two symbols to identify gravity or weight. Sometimes we can use an F sub g if it's just gravity in general. But if we're talking about gravity in terms of the weight of an object on a planet, then we can use a W, which is nice. Okay? Now, gravity always pulls towards the centers of the objects involved. For example, if you want to look at a large mass and you want to look at a small mass, a big M and a little m, the gravity exerted between those two masses is always measured from the centers. Okay? Center of mass is very important. That's the point where we could think all of the mass to be located, even though it's actually spread out a little bit. We know that. So, when we draw the gravity acting on this mass from this one, the gravity acts in this direction on that mass. This one is pulling it that way. This one is being pulled that way. Okay? Gravity always pulls towards the centers of objects. So let's talk about Earth now. If you're standing on the surface of Earth, then Earth is pulling you straight towards the center of the planet. But likewise, you're pulling up on the Earth straight towards the center of your own mass. Remember Newton's third law? Every action has an equal and opposite reaction. Newton's third law governs this. If you have two masses near each other, each will exert an equal and oppositely directed force on the other, in this case, the gravitational force. So, the gravity between these two masses is actually the same, and we're going to talk more about that later. The point being that it always pulls towards the center of the masses. So, on Earth, gravity always points straight down towards the center of the planet, which is why we draw the arrow that represents the gravity or weight on our free body diagrams straight to the bottom of the paper. Okay? Because if we consider the bottom of the paper to be the surface of the planet and the paper is in the upright position, then it's straight down. All right. Now, there are two ways to calculate the gravity between two masses, or if you want to call it the weight. We're going to look at the two ways, the short and long. I call them the short way. Here's the short way when we're looking at the weight, okay? When we're looking at weight or gravity between an object and a planet, we can use Newton's second law. This force, if that's the only force that acts on a mass, it will make the mass accelerate straight down towards the center of the planet. And that mass will have a special acceleration, the acceleration caused by gravity. Now, we know that is an acceleration. That is gravity. Don't call this gravity, okay? Gravity is not an acceleration, it's a force. This is a change in motion. Keep that in mind. In fact, you're going to have a whole discussion about this on Friday. So, let's take a look. On Earth, G has a value of 9.8 meters per second squared. More massive planets, G would have a larger value. For example, I believe on Jupiter, the acceleration due to gravity is like 25.2. On less massive planets, the acceleration would have a smaller value. In fact, on the moon, and we've used this before, it's about 1.63, okay? Now, why is the acceleration on different planets different? Well, because the planets have different masses, so they don't all pull the same on the same mass. So if I had a big cinder block and I took it to the moon is not going to pull as hard on that cinder block as the Earth would because the moon doesn't have as much mass. So its acceleration is less. On Jupiter, because it's much more massive, it can pull much harder on the cinder block and therefore produce a greater acceleration of like 25.2 meters per second squared. All right, now let's talk about mass and weight for a minute more. They are two different things. So let's look at what happens if we compare mass versus weight at two different locations. Let's suppose we have a 97 kilogram object on Earth, and we want to know what is the gravity of the object on Earth, okay? Well, don't write too big right here, there's not a lot of room. So here's what we would do. To find the gravity acting on this object on Earth, we'd say m times g, where the g is the acceleration on Earth. And I think I'm going to make that just a little bit bigger for right at the moment. Okay, so we're going to take 97 kilograms and multiply it by 9.8 meters per second squared. And if you stick that in your calculator, I think you're going to get 951 newtons. So this is the gravity or weight of that 97 kilogram object on Earth. Okay? Now, let's take our object to the moon. Look at this next question. It says, what would be the object's mass on the moon? Now remember, mass is the amount of matter something contains. All the molecules, all the atoms, all the stuff. So if we take the cinder block or whatever this object is to the moon, has it changed mass? Has the amount of matter it's made up of changed? No, it hasn't. So the mass on the moon is going to be the same as the mass on Earth, and that is going to still be 97 kilograms. It hasn't changed at all. So mass for an object is constant unless you physically change the amount of matter in the object by lopping off a part of it, okay? Part C, what would be this object's weight on the moon? Well, weight is gravity. It's the same thing. So to find the gravity or weight on the moon, we'd take the mass of the object times the acceleration on the moon, okay? So that would be 97 kilograms times 1.63 meters per second squared. And if you put that in your calculator, I believe you're going to get a value of around 158 newtons. Oh, wow, look at that. So the force of gravity acting on the 97 kilogram object on Earth is 951 newtons. But if you take it to the moon is only going to pull on that object with 158 newtons of gravity. Big difference, isn't there? Okay, so mass and gravity, two different things. And remember, this is not gravity. This is the acceleration, the rate of change in motion that the mass would have in free fall. Got it? All right. Now, hang on, let me see if I can turn my page here on my key so I know what I'm talking about when I look at it. All right. Let's take a look at the second way that we can talk about gravity. Now, what if the objects that we're looking at, what if they're not a planet and a smaller object? Okay, how would you find the gravity between, say, your dining room table and one of the chairs? They're both objects. They both have mass. That means they have an attraction for each other. Now, how big is that attraction? Well, obviously not very big because it's not enough to overcome their inertias and make them accelerate towards each other, is it? You don't see them slamming together. So that means the gravity is actually going to have a very small value, but that's because they're very small masses compared to planets. So how would we find the gravity between two objects like that? Well, Newton figured that one out too. So he actually had 4 laws, but we don't call this one one of the laws of motion. It just has its own name. It's called Newton's universal law of gravity. Okay? Newton's universal law of gravity. Now, what about the word universal? What does that mean? Well, it means exactly what it sounds like. You can use it anywhere in the universe between any two masses. You just have to know 2 things. First, you have to know the amount of mass each of your 2 objects contains, and you have to know how far apart they are. You see, gravity is actually a force that obeys an inverse square law. And what that means is, as the objects get closer together, the force between them gets stronger. As the objects get further apart, the force gets weaker. Okay? Kind of like 2 magnetic poles, right? You've held magnetic poles next to each other and felt the repulsion or the attraction, depending on the ends. You also know that the further apart they are, the less of that force you feel. The closer together they are, the stronger it feels. So it's an inverse square law. So let's see what it looks like. Newton said that gravity is proportional to, and notice I'm leaving a space here, you do too. It's equal to the product of the 2 masses in question divided by the square of the radial distance between them. Remember, we always measure from the centers of the 2 objects. So we're talking about the radial distance between their centers, okay? Now, he said it's directly proportional to the product of the masses and inversely proportional to the square of the distance between their centers. In fact, if we look at these 2 relationships, here's what we find out. Okay, now let me give enough room here so you can see. If we were to look at the relationship between gravity and the product of the masses, we would get a linear relationship. Both are in the numerator. Neither one is square. If we look at this as one quantity, both are in the numerator. Neither one is squared, so you get a linear relationship. If you double one mass, you double the gravity between the 2. If you split one mass into fourths, you split the gravity into 4th. Okay? It'll be a 4th of what it was. Let's look now at the inverse relationship between the gravity and the square. So here's what that's going to look like. So if we look at the radius, the radial distance, and the gravity, because the radius is in the denominator and the gravity is in the numerator, that's going to give us a hyperbolic or inverse relationship. And it's going to look like this, a hyperbola, okay? As the force gets bigger, notice the radius gets smaller. But as the radius gets bigger, the force gets smaller. That's what it means. When one increases, the other decreases, and vice versa. So the bigger the radius is, the smaller the gravity between the 2. Okay? Now, let's take a look at what this space means. Newton said that the gravity is proportional to this product and inversely proportional to the square of the distance. But he just said they were proportional. In fact, he sent his work on this to another scientist friend of his who asked for his opinion on how gravity works. And he just sat up one night and he came up with this. Man was a genius. He came up with this. He said there needed to be a proportionality constant to make the two sides equal, but he didn't have time to worry about that, so he sent it on. It was later left to an English scientist named Cavendish, who came up with a proportionality constant that we need to make the two sides actually equal to each other rather than just proportionate to each other. Today, we use the capital letter G to represent, and again, I think that's a mistake on somebody's part. They use the capital letter G to represent the universal gravitational constant. And it has this value because, again, it is a constant, just like Avogadro's number or the ideal gas constant R, okay? So it is a physical constant. It never changes. It's the same throughout the universe. You have to have it right there in the numerator and multiply it by this side so that it becomes equal to that side instead of just proportionate. Okay, now I do notice we have a blank right here that we need to take care of. It says R is the radial distance between the two masses. So from center to center along the radii. Okay, how do we use this? Well, let's take a look. There is an example right here, and we can look at that fairly quickly. Okay, checking my time. All right, I still got time. So, I did leave this out. That should say between their centers. I just noticed that. I'm glad I write these things down so I remember from year to year. One of these days I'll put that in there in the processor and then it'll be okay. All right, look at this example. It says, what is the gravity between the Earth and the Moon? Well, in order to find the gravitational force between the Earth and the Moon, we need some stuff. We need the mass of the Earth and the mass of the Moon because those are our two objects. We also need the radial distance between them. And now you might be thinking, well, Miss Pepitone, the Moon is not always the same distance from the Earth. Sometimes it's closer. Sometimes it's further away. Yes, that's true. But we can find the average gravitational force acting between them by looking at the average radial distance between them. And then simply know that sometimes it's a little more and sometimes it's a little less. So here's what we find out if we look up on the inside front cover of the textbook, or maybe it's on the back inside. I can't remember which on this new book. But the mass of the Earth is about 5.98 times 10 to the 24 kilograms. All right? And the mass of the Moon is much smaller. It's about 7.35, but that's bigger. Wait for the power. 7.35 times 10 to the 22. Now, what's the difference? 10 to the power of 2. So it's 100 times smaller, isn't it? Okay? It's 100 times. The Moon has a mass that's 100 times smaller. Okay, now, the average radial distance between the two, if you look that up, again, in the physical data that's in the, I think it's on a page on the inside back cover. And you can check that with your textbook just to see. 3.85 times 10 to the 8 meters. All right, now, we know the mass of our two objects, we know the average distance between them, and we know our proportionality constant. So now, here's the fun part. Guys, using this formula is actually very easy. The tricky part is getting all of this into the calculator properly. So look at what we have. We've got big G, mass of the Earth, mass of the Moon, over the radial distance between them squared. So we get this, look, 6.67 times 10 to the negative 11. Notice the units. It's got a lot of units. We're going to talk about that in a minute. Newton meter squared per kilogram squared. Times 5.98 times 10 to the 24 kilograms. Times 7.35 times 10 to the 22 kilograms. Divided by 3.85 times 10 to the 8 meters. Oh, and guess what the most common boo-boo here is? Forgetting to square the R. Okay, we got to remember to do that. So now here's what I want you to do. I want you to pause the video right now, And I want you to get your calculator and see if you can put this in and come out with the correct answer. All right? Then unpause the video or resume it and see if you got it right. Okay? Try it. All right. Now if you've had time to try to put that all in your calculator yourself and see if you can get the answer, let's see if you did. If it's put in properly, you should get 1.97 times 10 to the power of 20 newtons. Okay? Now, if you didn't get that, you need to go back in and see and carefully see if you can do it. Remember, don't use the actual buttons times and then 10 caret negative 11. Don't do that. Use the actual scientific notation button, okay? And then double check that on the bottom you did square the R, because that's the most common boo-boo there. Now, units. I want you to notice, why does this have so many units? Well, we have to get newtons from somewhere because we're solving for newtons of force. So there's the N. The meter squared is going to cancel with the meter squared that you get down here, okay? The kilogram squared on the bottom here is going to cancel with the kilogram squared that you get right here. And that will leave behind newtons of force, okay? Now that wasn't so bad, was it? Nah. All right, so tomorrow in your folder, you're going to see a discussion activity, and it is a type of assignment. You do get points for it. You're going to watch some videos on mass versus weight, because I've got to make sure you guys understand that. And it's going to talk about some different situations that I don't have time to talk about here. And then you're going to answer some questions. You don't write them down on your paper and scan and submit like you normally do. This is a discussion box, so all you have to do is type the answers into the comment box that's at the bottom of the discussion box. So that's all you have to do is type it right into the computer and then post. Now please understand, I will only grade the first post. I won't grade a second post. So make sure you do not hit post until you've fully answered each question the way you want. Only then hit post. Because if you accidentally hit post and you've not finished, sorry, that's the way it goes. I will only grade the first post. I will not grade a second or third one. All right, guys. See you soon. Bye-bye.